Hello. In today's video, we are going to discuss about the magnetic effect of electric current. Now, Oersted, in his experiment, had obtained that whenever a magnetic needle was brought close to a current carrying wire, so this is the compass having the magnetic needle, suppose, and it was brought close to this wire carrying current in the given direction as shown. It is a part of any given circuit, and when it was brought close to it, it showed a certain deflection. The pointer that you see over here, it showed a certain deflection. It deflected, uh, and he thus obtained the result, the conclusion that with this deflection you can say that the pointer should have been in a certain direction, but now the pointer is deflecting along a certain line, and with this deflection he thus concluded that there must be some magnetic field present in that given region. However, there was no permanent or there was no magnet of any form, artificial or permanent. So this led to the uh, result or the conclusion that he further concluded that obviously the current that was flowing was responsible in some way or the other for the production of a magnetic field. The magnetic field must have a certain intensity at a given point. The deflection here is not the same as deflection in any other point, as I show you by the markings. It will be different at different points, and therefore the intensity of the magnetic field that is associated with the current that is flowing through the wire, which may be a part of any given circuit, will be different, and that intensity can be calculated by knowing the Biot-Savart's law. The Biot-Savart's law simply states that if there is a current carrying conductor, it is carrying current along that direction as I show it. Supposedly, I have a point P where I want to determine the magnetic field intensity, because now we know that the magnetic field intensity, there's a certain magnetic field associated with the current carrying conductor. So the point P lies at a distance, say r. It lies, suppose, at a distance r, where r is its position vector, we can say, and we choose a certain elementary length dl. From that elementary length dl of the current carrying wire, this point lies or is positioned at a distance r, and so r gives its position vector with respect to the element dl. As per Biot-Savart's law, what we get is that the magnetic field intensity, usually represented by the symbol B, that is a vector quantity of course, but as of now we'll be dealing with the scalar part of it, the magnitude of it. The magnitude of the magnetic field intensity, that is directly proportional to the amount of current that is flowing across the conductor. It is also directly proportional to the elementary length, or the length that is considered here. The elementary length that we have taken is the differential of L or dl, and it is inversely proportional to the square of the distance. And then this dl, it has a certain direction, and this direction is along the direction of current. along the direction of the flow of current, and that is why dl will be directed along the tangentially at that point along the direction of I, that is in the upward direction as shown in the figure. So dl has that direction, r has that direction as shown. Between those two arrowheads we can have an angle which is theta in this case, and so it also states that it is directly proportional to the theta or sine of theta. We can have it as only theta, but eventually we'll find out that it is the sine of the angle on which it depends. There are various factors which lead to the conclusion that it will be sine theta and not cosine or tangent of that angle. We'll be discussing them gradually. Putting all of these together, what we obtain is that the magnetic field intensity in terms of its magnitude is directly proportional to I dl sine theta, and as it is inversely proportional to the square of the distance, so by r squared. And what we do is we replace it by a constant term in order to obtain the equality on both sides. So the constant term here that is associated with the magnetic field is the familiar mu naught by 4 pi, as we have discussed in magnetism and matter. So this is the magnetic field intensity. The magnitude of the magnetic field intensity is therefore equal to mu naught by 4 pi I dl sine theta divided by r squared. Now these terms that we see over here, because the length is small, so we can say this magnetic field will also be small. So instead of B, I write it as a dB. Instead of B, I write it as a dB. And we can have the entire magnetic field intensity by taking the integral of the term, where we have I dl sine theta divided by r squared. Now, the reason that I have the r squared and the sine theta term within the integral is what we are going to discuss now. The dl is a vector quantity. As we have seen, it is directed along the direction of the flow of current. Also, the position of the point P, that is a vector quantity. So r is a vector, dl is a vector. And when you have two vectors and the result of that is also a vector quantity, which is the magnetic field, we end up with a product known as the cross product. But here we have the division of those two vectors, but we can have the vector form in this way, where we can choose the unit vector of r. So if we are to choose the unit vector of r, so we end up with dl cross r cap divided by r squared, and the sine theta gets involved in that cross product, so we lose the sine theta there. It's present, but it's implicitly present, not explicitly as shown in the previous expression. So dl cross r, we can also therefore write this as mu naught by 4 pi I integration of dl cross, if we are to take the vector form, that is instead of the unit vector, if we take the proper r vector, then we have r cube over here in the denominator and r vector there at the top on the numerator, because we know that r cap is simply r vector divided by the modulus of r. That is how we define the unit vectors. So this gives me the Biot-Savart's law in complete form with the integration available to us. This is just the raw form of the Biot-Savart's law, the incomplete one, where we are just mentioning the magnitude as well as not the complete result. This Biot-Savart's law will help us determine the magnetic field intensity due to any conducting wire, the magnetic field intensity at any point due to any conducting wire in its periphery. So we straight away move to the application part of the Biot-Savart's law. So first up, applications of Biot-Savart's law. The first kind is the magnetic field at a point near a straight conductor carrying current. Now a straight conductor can be treated to be finitely as well as infinitely long. Infinitely long, that doesn't really mean that its length cannot be counted, but the thing is that when considered at a point, relatively its length is uh, quite large or quite long, so as to obtain any given angle. We'll see how it proceeds. So field at a point near a straight conductor carrying current, we'll treat it for the finite length first of all. Which is the acceptable way in terms of in a layman's language, is quite acceptable that we consider the length finite, but we'll see how the length goes to infinity when considered for that given point. So this is a wire which is carrying current, and supposedly it is carrying current in this direction, the upward direction. It can, however, go in the downward direction as well. You can take it. And we have the terminals at the top and the bottom being M and N. So Mn is that wire, and its length supposedly is Mn is equal to L. I denote it as capital L. We have the point P over here where we want to determine the magnetic field intensity. Due to the current carrying wire, it is carrying a current I. The current that it is carrying is I, and we can drop a perpendicular distance over to that point P. This is the perpendicular distance from the wire, and that perpendicular distance is let us say it is A, right? And it is directed, so A is the position of the point P with respect to a point O that is considered in the wire. With respect to a point O that is considered in the wire. So this is the point O. Now, with that done and dusted, what we do is we take another element that we are supposed to take. So let this element be dl. dl is that elementary length, and the distance from that elementary length is x. Let's take x being the position vector, and this distance of dl from the perpendicular point O is small l. Small l is the distance of the elementary length dl from that point O, and then the angle in this case is theta. We can consider another angle over here, that is for this point near the point P, and we take it as alpha. We take that angle to be alpha. With that angle being alpha, we can further take the upper points, the angle of the point P, or the angle that the point P subtends, with the uppermost point of the wire and the lowermost point of the wire is alpha 1. Let's take it as phi 1, and then we have this as phi 2 with respect to the perpendicular point, or with respect to the perpendicular OP. So with respect to that perpendicular OP, phi 1 is the angle subtended by the uppermost point at the point P, and the bottommost point N subtends an angle phi 2. So that phi 1 and phi 2 together covers the entire length of the given wire. Let us name the point here to be R. So we have a triangle now, OPR. So OPR, in that triangle, what we find is triangle OPR is a right angle triangle, of course, and we find that the sine theta that we are going to need for Biot-Savart's law, that is also equal to cos alpha, because the alpha is the other angle apart from the 90-degree angle. So sine theta here is equal to cos alpha, and that is eventually equal to which side by which side? Well, it is equal to the side OP divided by the side PR, that is A by X. So this is A by X, the value. And we also have a tan theta there, or a tan alpha. We'll be using that later. Now, as far as Biot-Savart's law is concerned, we'll be applying Biot-Savart's law to obtain the value. The reason why we need cos alpha will be given to you very shortly. As per Biot-Savart's law, we have the magnetic field intensity dB, the small magnetic field intensity to the small element dl, to be equal to mu naught by 4 pi I dl, and we are doing this in terms of magnitude. We are not concerned about the direction as of now. So mu naught I divided by 4 pi dl sine theta divided by r squared. Instead of r squared, we are having x as the variable over here, so x squared. Now what are the things that are going to change? If we were to integrate, we would have integrated over dl, but that's not the only thing that is changing over here. With varying the value of dl from the bottom to the top, or from the top to the bottom, we'll be varying the value of theta as well, and we'll be changing the value of x as well. So we need a single change in variable for us to integrate this thing quite easily. So in order to do that, what we need is a certain amount of substitution is required. Now the L that we see for the length, the dl part is the small the differential of the length. What we can have is that we can try that variation of dl with respect to the angle because we can integrate. The reason that we took these two angles over here is that we can obtain the value or the integration when we are varying with respect to d alpha instead of dl. And d alpha can vary because alpha is that angle of that the points are making with respect to p. The total length of the wire that is being covered by the angle alpha from phi 1 to phi 2 can be easily achieved or can be easily calculated. We'll see how. So tan alpha, if you see, is equal to, tan alpha will be equal to L in the triangle OPR. Of course, it will be L divided by A, right? Or L is equal to A tan alpha. To put things easier, in an easier way, dl is equal to A tan alpha is simply sec square alpha, the derivative of it, times of d alpha. So we have got the d alpha for the dl, and we also have the value of x that is going to vary from this equation that is over here. Since a sine alpha is equal to sine theta is equal to cos alpha is equal to a by x, what we get over here is that x is equal to a times of sec alpha. X is equal to a times of sec alpha, and we can put all of them in this equation that is available to us. That is the Biot-Savart's law. So what we get is, I rewrite the equation over here, dB is equal to mu naught divided by 4 pi I. So we have converted everything into alpha, and then we'll be setting the limits for alpha from the topmost point to the bottommost point in terms of the angle. Mu naught I divided by 4 pi. Instead of dl, we have a sec square alpha d alpha. Instead of sine theta, we have the cos alpha term, so we write it as cos alpha over here, divided by the value of x being equal to a sec alpha, so we have a squared sec squared alpha. As you can see, a lot of things can be cancelled over here, especially sec square alpha at the top and at the bottom gets cancelled. One of the a's can get cancelled, so what we are left with is mu naught I divided by 4 pi a is a constant, and what we are left with is cos alpha d alpha. Now this is pretty easy to integrate on. So dB is that value, so B is simply the integration of dB, and the integration is being taken from the lower alpha to the higher alpha, or the lower region n to the higher region m. Well, the angle that we have taken over here, that is phi 2, well, phi 2 is simply we can take it as a matter of sign convention to be negative because of the because it is lying, if O here is treated as the origin, and we are taking them as the axis. So we have the bottom axis and the top axis, the bottom axis being negative and the top axis being positive. That is how we are taking the sign convention over here. It's easier that way. You'll know how. So it is from the bottom to the top, that is from minus phi 2 to plus phi 1 cos alpha d alpha. Now obviously the integration of cosine is going to be sine just positive sign. So this is sine alpha taken from minus phi 2 to plus phi 1. And this will be mu naught I 4 pi a sine phi 1 minus upper limit minus the lower limit sine minus phi 2. As you know, sine is an odd function, so this is mu naught I divided by 4 pi a sine phi 1 plus sine phi 2, which is the magnitude of B. Now, if we are to consider the direction in this case, the direction obviously is going to be dl cross r as far as Biot-Savart's law is concerned. The r we can use instead of the x value x that we have taken for r for that elementary length dl. We can choose the entire length and we can choose a as the fixed value. So the direction of dl or L is from N to M, that is along the direction of flow of current, and A is the direction or the position of the point P with respect to the given conducting wire. And so we have this as the direction of L and this as the direction of R. So L cross R, the cross product is going to take us into the plane. Now, if the point P was onto the left hand side of your screen and that is on the other side of MN, then the L cross A would have been out of the plane. If had it been on the back side, then L cross A would have been on the left hand side. You can see for yourself by using the cross product rules determining the cross product. And had it been in front of MN, that is out of the screen towards you, hanging between you and the length MN, then it would have been to the right hand side, DL cross A. You can check for yourself again. In case you are finding it difficult, you can use the right hand thumb rule and you can refer to the previous videos that I have made on vectors. So likewise, if you observe for a current carrying wire, so suppose this is the current carrying wire and is carrying the current in the upward direction, then the magnetic field is encircling it like this. Here it is into the plane, here it is out of the plane, here it is along this direction, here it is along that direction. So it is just spiraling about. If the points are considered on that spiraling plane, then it will be along a circular path. So that means that if you are using your right hand and you have the thumb along that direction, which represents the direction of flow of current, then your fingers that you will be curling will be giving you the direction of the magnetic field in which it is moving, here, along this, along this, along this. So this is the thumb rule of determining the direction of the magnetic field intensity. On the right hand side it will be on the into the plane, on the backwards direction it will be to the left, on the west direction, that is on the left, it will be coming out of the plane, and on the front side it will be going towards the right. Likewise, if the current is flowing in the downward direction, similarly you can align your thumb of the right hand. So the right hand thumb can be aligned along this direction, and what you'll find is that the magnetic field is simply moving like this, the order in which I took it. So it will be here, on this side it will be into the plane, On this side it will be towards the right, on this side it will be coming out of the plane. So similarly, you can very easily choose the direction or obtain the direction of the magnetic field uh, associated with a current carrying conductor. Now comes the case of infinite length. Well, uh, it's hard to imagine the infinite length, but I'll tell you what. We can consider the case of current being drawn through wires across your street. The wires are pulled across long distances, and you just imagine a point alongside that wire where you have to obtain the magnetic field. Now, considering the length of the wire across the street, obviously that point is just a fractional part of that length, and that is why, although the wires are finite, but we can however consider them to be infinitely long, where the lengths are incomparable. So incomparable lengths are what we term as infinite length, where the lengths cannot be compared really. So this wire is infinitely long supposedly, and it is carrying the current in that direction. We are to obtain the magnetic field at a point P. We have already obtained this, but the only difference in this case is that the angle that we are going to take for the topmost and the bottommost point, the topmost point is continuing and the bottommost point is also continuing. As a result of that, the angle is going to be somewhere very negligible, very big, not negligible, my bad. The angles are going to be very big, almost close to the 90-degree angle when considered with the perpendicular. The angles are almost 90 degrees, which is wise to take it as 90 degrees completely. So the value of B in terms of magnitude was mu naught I divided by 4 pi A being that perpendicular length from that given wire, and we had ended up with sine phi 1. In this case, the phi 1 is 90 degrees, and the other angle as well is tending to 90 degrees. So sine 90 is 1, 1, 1 plus 1 is 2, and the 2 gets cancelled with the 4. So what we get is mu naught I divided by 2 pi A. The direction obviously is as I had discussed in the previous page. So this is the value of the magnetic field intensity for an infinite length. Now, in case of an infinite length, because we are not comparing the lengths, these two sides, this side and the bottom side, well, they are infinite, because at the top it is continuing to infinity and at the bottom it is continuing to infinity as well. So this line can be treated, however, as a perpendicular bisector. So in case that we have a finite length, and the angles phi 1 will be equal to phi 2 for sure, and let that be equal to some angle phi. In this case, the angle phi is equal to 90 degrees. Phi 1 is equal to phi 2 in this case as well, and that is equal to 90 degrees. But for a finite length, if those angles are equal, we will say that let those angles be equal to phi, a common angle, that is, because they are along the perpendicular bisector, so the angles must be same. So as a result of that, what we get is that B now is equal to mu naught I divided by 4 pi A, and in the brackets we have sine phi plus sine phi, the other angle. So this is 2 sine phi. The 2 can get cancelled with that 4 to give us 2 in the denominator, and we have the sine phi with us. So this is how we obtain the magnetic field intensity due to a current carrying wire, and if the point lies at a perpendicular bisector, and this is due to a straight conductor. In the upcoming videos we'll be discussing about the magnetic field intensity due to circular coil carrying current at its center as well as along its axial line. Before that, I would like to end this video with a numerical for you. Let us say that we have a wire in the shape of a square. This is a part of a circuit, and it is of length A, suppose, and it is carrying current I. In that sense, that is in the clockwise sense over here, we wish to determine the magnetic field exactly at the center, which is obviously the point where the diagonals bisect for the given square. So we wish to obtain the magnetic field at the center, let that point be O, magnetic field along with the direction as well. So we wish to obtain that. Well, I'll give you a hint how you can proceed. Now, because the magnetic field is a vector quantity, due to this wire you'll be having a certain magnetic field at this point, let that be B1. Due to this wire you will be having a magnetic field at the center, which is B2. Similarly, for the rest of the sides you will be having B3 and B4, and this is an easy one, so you can calculate it with ease. So B net, that is the net magnetic field at the center that is supposed to be determined, is actually the vector sum of the individual magnetic fields as far as the principle of superposition of the vectors is concerned. So you use the principle of superposition over here and you obtain the net magnetic field at the center. Remember, if the magnetic fields are oppositely directed, they will simply cancel out each other, and if they are in the same direction, they will add up directly, which will be the case over here. So I have given you a lot of hint for the given problem. You just have to obtain the expression for the magnetic field at the center. Some of you might have finished the answer as well before I have ended the question, which is great. Till next time, thank you for watching.